Hi, my name is Daan van Aken and I'm currently doing a master's in aerospace engineering. Last year I was a structural engineer in the Delft Hyperloop team, and today I will tell you about the structural aspects of the chassis of a Hyperloop vehicle, while also shortly discussing the aerodynamics. The chassis of the Hyperloop is the main body structure to which all other subsystems are attached. Therefore, its main function from a structural point of view is to allow all these connections while also being able to transfer and withstand forces between them. Additionally, the chassis carries the passengers, keeping them safe and allowing them to embark and disembark, much like the fuselage of an aircraft does. The interior and passenger experience will be covered in a different lecture. Today's lecture will focus on the structural aspects of the chassis. As mentioned, the structural function of the chassis is to transfer forces between subsystems. For example, when the vehicle brakes, the forces from the brakes are transferred to the chassis by means of suspension. The chassis must then transfer the forces to all other components such that they do also decelerate. Then the important question for most of the chassis is, what are the most important forces? As you might expect, there are forces from propulsion and from braking. Additionally, the masses of everything attached to the chassis exert forces due to gravity or due to accelerations or decelerations exerted on the vehicle. There might also be bumps in the track which cause forces, much like those you would feel from a speed bump when driving over it in a car. Finally, one of the most important forces is that of the pressure difference. Just like in an aircraft, the air pressure inside the cabin is the ambient pressure, as around us right now. However, the pressure in the tube is of course very low. This pressure difference causes a large force on the entire chassis, which separates the two different pressure environments. A way to design for this pressure is very similar to the one used in the aircraft industry. A circular body is the most efficient way of dealing with these pressures and is therefore widely used. Before we look into the influence of the shape of the vehicle on aerodynamics, I will shortly discuss the options in terms of material and structural design suitable for the Hyperloop. The two most promising materials are aluminium, as was standard for in the aircraft industry for the past century, and carbon fiber reinforced polymers, which are becoming increasingly more popular in both the automotive and aerospace industry today. Both are selected because they are relatively strong and stiff compared to their density. This means that the design can be light while also being able to withstand all the forces. Carbon fiber reinforced polymers consist of a very thin threads of carbon which are kept together by a layer of plastics, a polymer, hence the name carbon fiber reinforced polymers, as you can see on this panel. This has the benefit that you can place the fibers in the directions in which the forces are directed, without also strengthening other directions, as would happen with aluminium. This means that carbon fiber can lead to an even lighter design compared to aluminium. However, it is a much more expensive material to use. As you can imagine, just stacking material until your chassis is strong enough would mean the skin would become very thick. There are two main ways to make the skin more efficient. The first one is a honeycomb panel, as can be seen here. It places a very light, relatively thick layer of material between the two layers of skin, making it much more resistant to the bending of the skin. The second is the panel I showed before, which has small beams along the skin called stiffeners. These provide a skeleton for the skin to stiffen it. The choice between these two strongly depends on the shape and design of your chassis. The design, especially the shape of the chassis, also plays a role in the aerodynamics of the vehicle. As the pressure in the tube is very low, the shape of the nose of the vehicle is not very important. What is much more important is the ratio between the diameter of the tube and that of the vehicle. This is because the Hyperloop itself reaches speeds close to that of the speed of sound. Because the air is accelerated when moving around the vehicle, the air around the vehicle will move faster than the vehicle itself, and therefore it will reach the speed of sound before the vehicle itself actually does. When this happens, the air around the widest part of the vehicle cannot move faster than the speed of sound by laws of nature. This means that the air cannot flow through the gap fast enough, meaning that a pocket of air will be built up in front of the vehicle, increasing the pressure and therefore slowing it down. The speed at which this happens is called the Kantovic limit, and it's one of the biggest remaining limits for the Hyperloop. After the widest part of the vehicle is passed by the air, shock waves will start to form. This is because the air will reach the speed of sound. These shock waves make up a large part of the aerodynamic drag of the vehicle. By designing a clever shape of the body and its tail, these shock waves can be kept to a minimum. This is why the design of the shape of the tail is much more important than that of the nose. And on this slide you can see some examples of nose and tail shapes which were thought of during our design. So to conclude, today we have learned the function of the chassis, which is to transfer the loads and carry the passengers. You've seen two possible materials, aluminium and carbon fiber. And finally, you know how the shape generally influences the aerodynamics of the Hyperloop.